Welcome to you all. So, in the last class we started module 3 relations among yarn count, twist and diameter. So, as I told you in the last class, the relations among yarn count, twist and diameter are related to specific geometrical and mechanical behavior of yarns. The underlying variable which governs this relation is packing density, fiber packing density in yarn. Now, the very first traditional model on the relations among yarn count and twist was found by Coughlin in the year 1828. He, based on two important assumptions, proposed the relationship. However, experimentally we observed that Coughlin's model was not too precise. Then many researchers in the area of yarn structure proposed many relations related to yarn count, twist, but all relations were empirical only. The question that remained is it possible to theoretically derive a relation among yarn count, twist and diameter, so that we can predict beforehand and then accordingly we can set our yarn manufacturing process parameters. So, with that aim we started a model, simple mechanical model. In the last class you learned that this model was based on 4 primary assumptions and one important assumption. Then we derived an expression for centripetal force per unit volume of the fiber. Then we were analyzing where the compression zone is situated inside the yarn, that we have analyzed in the last class, and then we also analyzed the total centripetal force in the compression zone. So, that was the final results in the last class. Now, we assume that this centripetal force P acts on a cylinder which is situated at radius r. That means, what we do, all the partial centripetal forces we centralized at one particular cylinder that is situated at radius r, where the centripetal force P acts. What is the surface area of that cylinder? Surface area A 2 pi r into L. So, what is the pressure developed in the compression zone? This pressure P is equal to the total force capital P by this area. So, this force is this, area is this. So, let us write it F sin square beta 2 pi a times L into mu by 2 pi r L s, right. So, these 2 cancel out, pi also, L also. So, what you obtain is that f sin square beta a into mu divided by r into s. So, f sin square beta by r into s a into mu. Okay. So, this is the expression for the pressure developed in the compressing zone. Now, what is difficult to obtain is the F, that is the axial force on the fiber. So, we have to find out a suitable expression for the axial force acting on the fiber, capital F. So, because of the insertion of the twist, fibers are inclined. So, if this is the yarn axis, let us think a fiber which is inclined at an angle beta. So, along the axis of the fiber, force F is acting. Along the axis of the yarn, a force F subscript A is acting, and this is the transverse force F subscript T, right. And what is this area? This is not cross sectional area, this is sectional area. Sectional area we denote by S superscript star, right. Now, what is your relation between this S star and S cos beta? This we have already derived in module 2. Okay. And what is the relation between F A and F? F A is F times cos beta. So, what is the normal stress act on the fiber? Sigma. Sigma is F A divided by S star, right. So, what is F A? F cos beta divided by S by cos beta. So, F by S cos square beta, right. So, what is F? F is sigma times S divided by cos square beta. Okay. Then we come back to our original expression of pressure. So, this pressure was F sin square beta by r into S A into mu. We substitute F from here. So, what we obtained is sigma S cos square beta sin square beta r into s a into mu, right. So, only this s is probably getting cancel out. So, as a result what we obtain is sigma a mu tan square beta, right. Now, what is tan beta? Tan beta is 2 pi r z. So, what is this tan beta? 2 pi r z square, right. So, if we substitute, we obtain sigma a mu 2 pi r z square, right. Now, we have to work on this expression P. P is sigma a mu 2 pi r z square. Okay. Let us write it in this manner: 2 sigma a u by d into 2 r by d, that means this cancel out, into pi d z, this into 2 r by d squared. Right. Two sigma a u into d by 2 r by d pi d z square 2 r by d square. So, what do we see here? So, this is the expression for P. Now, what we see, this d is equal to d s by square root of mu. 2 r by d, let us remain this is equal to kappa. Okay. So, 2 sigma a times mu by d s by mu, then your kappa square and 2 r by d, is not it? Okay. Two sigma a u by d s by mu and kappa square 2 r by this. Further, we write it as 2 sigma a 2 r by d within bracket root over mu, then 1 by d s, right. And then kappa mu kappa squared by 4 pi into 4 pi. Why do we write in this manner? Because this is equal to alpha s square. So, that is why we write in this manner. So, finally, what we see, 8 times pi sigma a 2 r by d root over mu alpha A square by ds, isn't it, right? By ds. So, now this A, so let us write this expression in another form. So, what we obtained P 8 pi A sigma 2 r by d root over mu alpha s squared by ds, right, ds. We obtain this. Now, 8 times pi into sigma, then this A by small d. So, we introduce small d, then 2 r by d root mu. Now, this alpha s squared ds by small d. Okay. Now, what is ds by small d? This is equal to tau, relative fineness, tau. So, finally, we obtained 8 pi into sigma A by d 2 r by d root mu squared by tau. Right. Eight sigma this A by d 2 r by d root mu alpha square ds by this tau. So, we obtained over tau. Okay. Now, let us consider this ratio is equal to capital C. So, we can then write pressure capital C root mu alpha square by root over tau, where C is 8 times pi sigma A by d 2 r by d. Okay. Clear? Now, let us learn about this ratio C. C is 8 times pi rho A by d 2 r by d. What does it indicate? What is the physical meaning of C? That is what we need to learn. Okay. Now, what is this 2 r by d? 2 r by d, we assume it is constant, because if d is increasing, let us assume r is also proportionately increasing. If d is decreasing, then r is also proportionately decreasing, so that this 2 r by d remains constant. Okay. Sigma is the axial stress in yarn cross section. Axial stress in yarn cross section can also be a constant, because the centrifugal force in spinning is perhaps the same. The centrifugal force in spinning is perhaps the same. So, sigma can also be considered to be a constant. Then you have A by D. What is this A by D? A by D is the relative thickness of the compression zone. Relative thickness of the compression zone, right. Let us assume this is also a constant. In that case, your C will be a constant too, right. So, C is a constant. It is very difficult, probably impossible, to measure experimentally the value of C, right. So, what is our result? Our final result is P is equal to C root mu square by tau, right. So, important relation, P is the pressure in the compression zone. How much pressure is developed in the compression zone because of twist, which is related to packing density, alpha s twist coefficient or twist multiplier, right, and tau relative yarn fineness. So, yarn tex by fiber tex. Now, if that means what? If you try to increase twist multiplier, then your pressure will be increasing and vice versa, right. So, this is a very important relation. We need to work on this relation later on. Okay. Now, we think about a very similar situation, which is often talked about in the book of mechanics. Two-dimensional homogeneous stress. So, this is fibers in the cross section of yarn and the pressure is acting on all directions. So, it is homogeneous stress. Then it is possible to derive that this pressure P is a coefficient K P times B mu cube by 1 minus mu by mu maximum to the power 2 plus A, and then this 3. So, it is possible to derive this relation. We are not going into the detail of this derivation, it is possible to derive this expression. So, P is K times P, it is basically a coefficient, B is another coefficient, mu is packing density, mu m is the maximum packing density. Typically in yarn, mu m is considered to be 0.8, practically we have seen this. So, mu m is considered to be 0.8 and A is found to be 1. So, this relationship we can later on think about that, mu m is 0.8 and A is 1. Now, we will compare our this equation with our earlier derived expression. Our earlier derived expression was C times mu alpha s squared by root over tau, right. Now, what we will do? We will make these two equations equal. So, K p times b mu cube by 1 minus mu by mu m 2 plus a cube is equal to C times mu alpha a square by tau, right. These two are equal to pressure. So, they are equal. Now, what is your alpha s? C times mu alpha s is equal to z root s. So, z root s squared, right, that is your alpha s. And what is tau? Tau is your root over yarn fineness by fiber fineness. This we learned, these two expressions we learned in module 2. Okay. So, this is equal to C mu. Now, z root s. So, okay, let us write it small t by capital T. Now, z root s, what is s? S is root over t by rho. This also we learned in module 2 square. Okay. Now, C root mu t by capital T z square t by rho. Okay. So, what we see is that C root over mu small t is fiber fineness. Now, that is equal to d squared then pi rho by 4, that is your fiber fineness, and z square root t by rho. Okay. So, what we see is that root over mu, then your C right, then this d will come out, let this d come out of the square root, then root pi will remain there, and 4 square root, that will be 2, and 1 root row will remain here into z square root t. Okay. Now, we will substitute this expression here and make these two equal. So, how will you do that? K p into b mu cube by 1 minus mu by mu m 2 plus a 3 is equal to root mu into C d root pi by 2 root rho z t half to the power 4 squared. Okay. So, what we did? We have derived this right hand side is equal to this, and then we substitute this in place of here, and we obtained this expression. This is t to the power 1 by 4. Okay. Now, if we little make it in a better manner, say mu to the power this square root 2.5 divided by 1 minus mu by mu m to the power 2 plus a cube is equal to C d to the power pi by 2 root rho, and this K p and b will come K p and b. This is 1 z t to the power 1 by 4 squared. Okay. Now, let us consider this is equal to q. Now, what is q? Q is a parameter. Parameter depends on C, D fiber diameter, rho fiber density, Kp coefficient of compression, and B another coefficient. So, q depends on material and technology. Why material? Because D is fiber material, rho fiber density, and why technology? Kp will be influence of technology, B will be influence of technology, capital C will be influence of technology. So, basically Q depends on material and technology. As of now, it is impossible to find out the value of Q experimentally, because lot of parameters are unknown. Kp is unknown, B is unknown, C is also not well known. So, it is not possible to determine experimentally the value of Q. However, it is possible to find out value of Q by some other means that we will discuss today. Well, then we will write the final expression here, mu to the power 2.5 1 minus mu by mu m 2 plus a 3 is equal to q z t to the power 1 by 4. This is the very important one of the two final expressions. One of the two final expressions. Right. Now, let us talk about these parameters mu m and a. Typically, maximum packing density practically in a yarn is equal to 0.8. We are not talking about theoretically maximum packing density, that is one, but practically maximum packing density in a yarn in one of the region is 0.8 and this A is typically 1. So, then this relationship will become this. Okay. Now Q is a parameter. For different technology, the value of Q will be different. For different fibers, fiber materials, cotton fiber, polyester fiber, viscose fiber, within same technology, say carded ring yarn, Q will be different. So, we will inform you about the value of Q for different fibers, different technology. Suppose now, if you know the value of Q, you know which count you have to produce, capital T, and you know your targeted packing density mu, then if you solve this equation, you will be able to know how much twist is required, capital Z, right. Say this equation can also be read in a different way. The value of Q will be given to you, Z, suppose how much twist has been inserted to the yarn, you know, what is the count of the yarn, you know. So, if you find out this value and if you solve this equation, the root of the equation, you will find out mu. So, packing density will be known to you. So, this equation can be practically applied for different purposes, but before going to that, let me tell you the value of Q. As far as the experimental results were concerned, the value of Q were obtained value of Q. What is the unit of Q? This is the unit of Q. Okay. Now, say fiber, and then we will talk about the density of fiber. Density of fiber we will talk about in this unit, and then spinning technology. Spinning technology we will talk about combed, we will talk about carded, and we will talk about rotor yarn. Okay. Fiber, say cotton, typically the density of cotton fiber we consider 1520 kg per meter cube. Then viscose, viscose fiber density we consider 1500, polyester, polyester 1360 kg this, and then wool 1310. The value of Q for combed ring yarn for cotton. This is the value of Q for combed ring yarn cotton. For carded for -8, and for rotor 8, right. So, this is the value for viscose. Now, let us start with viscose. the value for viscose is viscose. So, the same basically, because we do not comb viscose. So, 1.76 into 10 to the power minus 7 for viscose, right. For polyester, when you consider 1360 kg per meter cube density, then polyester also will be same value for carded and combed for obvious reason. For rotor yarn, this, but for wool minus 7, 1.20 into 10 to the power minus 7, 6.49 into 10 to the power minus 8. Right. Now, show this table, suppose you have, now you know the value of Q for different fiber material and for different spinning technologies. What is the value of Q when we produce rotor yarn using polyester fiber? This value 1.29 into 10 to the power minus 7. What will be the value of Q when we produce carded cotton ring yarn? 9.61 into 10 to the power minus 8. Okay. So, if you know the value of Q, you will be able to find out the expression mu to the power 2.5 divided by 1 minus mu by 0.8 to the power cube is equal to q z squared t to the power half. Okay. Now, so as I told you before at the beginning of this module, that in any theoretical work the final expressions are often compared with the experimental results. You have obtained this final result. Obviously, this final result is based on certain assumptions. When we compare this expression with experimentally obtained results, if they are matching, probably our assumptions were close to reality. If they are totally different, then probably one or more of the assumptions were not close to reality. So, we have to change those assumptions, we have to modify them, and we have to again rebuild the model. We have to find out the final expressions once again, and we compare with the experimental results. So, that is how the theoretical, this is a typical character of any theoretical work. So, now we obtain the final results, now we would like to compare with the experimental results. This is the comparison. Comparison between theory versus experiment. So, a lot of yarns, also rovings, were prepared by using different yarns were produced. Those yarns were carded ring yarn. carded cotton ring yarn. So, the value of Q 9.61 into 10 to the power minus 8 meter square takes to the power minus 0.5. Now, those yarns twists were given. So, twist value of the twist were known, fineness of the yarns were measured, and also those yarns, the cross section of those yarns were analyzed to find out packing density mu, average packing density mu. Okay. Then those experimental results were plotted in a graph. This graph is shown here. Along the x axis, z t to the power 1 by 4 is plotted. Along the y axis, mu is plotted. So, for different experimentally obtained results, you see hollow circle, positive sign, right. So, all these are experimental results for yarns were produced. Then using this value of Q, using the value of Z experimentally measured and also the experimentally measured value of T, the right hand side was calculated for different yarns. Then this equation was solved and we found out different values of mu. This solid line, thick black one, obtained from theory. So, this line was obtained from theory and all these are experimental points. So, how we obtain this line? We solve this equation. Q we considered 9.61 into the power minus 8, Z we measured the yarn count, we measured the yarn twist. So, for one yarn this value was known, we solved this equation, we found out mu. For different values of Z, for different values of T, we found out many values of Q, mu. We plotted all those values and we obtained this thick black line curve, that is from theory, and these are the experimental values. What we see is that this curve matches quite well with the experimental results. So, that means this equation what we derived, what it talks about relation between yarn twist, yarn count and packing density is probably a very well expression. We can use it in practice, right. Then how will you find out diameter? Now, diameter is known by this form rho. If we obtain mu, if we substitute mu here, T is already known, fiber density is known, we can find out D. So, how we can use these equations in practice? Now, this we have to learn, because we have to finally apply this equation. Suppose we have to produce a cotton carded yarn of given fineness. So, capital T is known, cotton carded yarn, and if it is cotton fiber we will know, and it is cotton fiber. So, we know value of Q. Suppose the packing density is targeted 0.46. So, the left hand side we will come to know, right hand side Q is known, capital T is known, we will find out Z. So, that much of twist we will insert. Okay. Also for research purpose you can use it in other way. How is this? Cotton carded ring spun yarn you have produced by giving say certain amount of twist, and yarn fineness is also known. So, capital Q is known to you, capital Z is known to you, capital T is known to you. So, right hand side you will be able to find it out. You solve this equation, you find out mu, that mu you substitute here, you find out capital D diameter. So, the relation among yarn twist, yarn count and yarn diameter you can find out. So, as I told you at the beginning of this module, packing density is the variable which governs this relation. You see in both relations packing density is significantly present. So, basically packing density is the variable which governs these two relations, relation among yarn count, yarn twist and yarn diameter. Now, let us solve a numerical problem to understand it in a better manner. This numerical problem reads as follows: a cotton carded ring spun yarn of 29.5 tex count. So, capital T is given, 29.5 tex, and twist is also given. Meter inverse is prepared. Estimate the packing density and diameter of this yarn. So, we will now demonstrate you how we can use the previous equation to solve this problem. Okay. Now, it is cotton carded ring yarn, right. So, cotton carded ring yarn, using this table we can find out cotton carded ring yarn, the value is this. Okay. So, Q we will consider 9.61 into 10 to the power minus 8 meter square tex to the power half. Okay. So, mu to the power 2.5 by 1 minus mu by 0.8 cube whole cube is equal to q z square t to the power half. Q you will substitute this value, z you will substitute 719.43 meter inverse, and t you will substitute 29.5 tex. So, as a result what you obtain is zero 0.2702. So, you will obtain this value 0.2702. So, this expression is equal to 0.2702. How will you find out mu? Mu can be found out by two ways. One, numerical method. You can find out the value of mu from this equation by using a suitable numerical method. Otherwise, you can also find out mu by already prepared a table. What does that mean? Suppose beforehand you will prepare a table where mu and this will be known to you. Suppose mu 0.38, okay. You substitute mu 0.38 here, you will find out the value 0.1251. Similarly, 0.39 you will find out 1374, 0.40 you will find out 0.1511, 0.41 you will find out 0.1661, 0.42 you will find out 1827, 0.43 you will find out 0.2012, 0.44 you will find out 0.2217, 0.45 you will find out 0.2446. The value you will find out 0.2702, 0.47 you will find out this value 2989, 0.48 you will find out this value 3312, 0.49 you will find out this value 3678, 0.50 you will find out this value 94. Suppose you produce this table beforehand. Now, what was the value? 0.2702. So, this is the value 0.2702. You will find out where this 0.2702 comes. Here you see 0.2702 has come. What is the corresponding mu? Corresponding mu is 0.46. So, you come back to this chart and then write mu is 0.46. So, you find out the packing density, right? Clear? Now, how will you find out diameter? Diameter is root over 40 by pi mu rho, right? Now, sorry, what is your 4? 29.5 tex divided by 3.14 into 0.46 into 1520, right. So, you will find out this value as 0.2308 millimeter. Clear? You will find out 0.2308. So, in this way this problem can be solved. I hope it is clear to you. In the next class we will continue with this module and solve one more numerical problem. Thank you very much for your attention.